Hello mathematicians. Today we see a nice problem asked in NBHM PHD 2020. It's about row equivalent matrices. Okay. So let A be a 5 by 5 matrix which is row equivalent to this 5 by 5 matrix R. Okay. Then we want to understand about first two rows of A, last four rows of A, similarly first two columns of A and last four columns of A. Okay. So before seeing the options, whether they are true or false, first quickly see what are the elementary row operations. Okay. So a matrix is said to be row equivalent to another matrix if they have the same row space. Okay. That is one definition. In other words, this matrix R can be obtained from the matrix A by sequence of elementary row operations. That is also another definition. So what are the elementary row operations? So you can exchange the ith and the jth row. This is a very important operation. So basically you can switch any two operations. Okay. So if you can switch it to operation, that also means that you can put any row in any other place you want. Suppose I want to change the first row to second row and the second row to third row and the third row to the first row. I want to do this permutation of rows. Okay. Then this corresponds to this permutation. 1 goes to 2, 2 goes to 3, 3 goes to 1. If you write this permutation as a product of transpositions, this is a 3 cycle 1, 2, 3. So if you write it as a product of transposition, you get 1, 2, 1, 3. Okay. Now let's see how to obtain this permutation of rows by swapping two rows at a time. Okay. So this suggests that first you swap first and so we have to operate from the right because the composition is done from the right usually, because f composition g of x equal to f of g of x. So first you have to apply g, then you have to apply f, right? So for that reason we first apply 1 3. Okay, so 1 3 means that 1 3 means that you swap 1 and 3 and you keep the 2 as it is. So we get 3 2 1. Okay, next this 1 2 says that whatever in the place of 1 and 2 that has to be switched. Okay, so we get 2 3 and whatever in the place of 3 that remains as it is. So overall 1 goes to 2, 2 goes to 3, 3 goes to 1. Okay, so by interchanging first row and third row, first you interchange, then you interchange first and second row in the resulting matrix. This will give you this kind of row permutation. 1 goes to 2, 2 goes to 3, 3 goes to 1. So this is because this transposition generates the symmetric group. So this is a, for example, this is a transposition. So what happens is any permutation of rows can be obtained by using this elementary operation. Therefore, by using row elementary operation, you can make any rows go anywhere. Okay, therefore the positions of the rows is not important. Okay, so any row can go to any set of rows, go to any set of rows. Okay, for example, if I pick these three rows, I can make it go to any three different places. Okay, so that is what this is explaining. So that is our first observation. Second thing is, let's come to this row operation. So if you apply this row operation, what happens is the positions of the rows, it's not going to change. Every row going to change in its place, but only the ith row you're going to multiply every coordinate. Ith row, every entry you're going to multiply by lambda. So now what happens is, if you look at the new matrix, suppose this is my original matrix. If I multiply it by 2 in the third row, so this every entry will be, this is 2, this is minus 2, this is minus 2. That's what we'll get. So what this does is it changes one row, but what it doesn't do is the row space, the vector space spanned by rows of this matrix, that won't change. That is because span of vectors v1 etc vk is equal to span of, I just multiply one vector by lambda keeping other vectors as it is. Okay, so this will not change the span. Okay, span of v1 v2 etc vk equal to span of lambda times v1 comma v2 etc vk. So that is the reason. So this vector doesn't change the row space. Row space means span of the row vectors. That is what we call row space. Similarly, this vector also what it does is it will change only the ith row. Remaining rows remain its place, and in the ith row we are doing some changes. We claim that this row operation also will not change the elementary, it will not change the row space. Okay, so basically what we have to prove, we have to prove that span of, for simplicity we take only two vectors. Okay, so v1 and v2, span of v1 v2 equal to span of like lambda v1 plus sorry, v1 plus lambda v2 comma v2. Okay, so in some vector I am adding the scalar multiple of another vector, and the other vectors I am keeping as it is, right? If you do this operation, that what it happens. We claim that span of this vector equal to span of this vector, but it is just straightforward to check. Maybe I can show you the quickly show you the calculation. So we claim that span of these two vectors is equal to span of these two vectors. So if you look at the span of this vector, this is alpha ri plus beta rj such that alpha beta belongs to R. If you look at the span of these two vectors, this is alpha time first vector plus beta time second vector, where alpha beta belongs to R. If you simplify this, you get alpha ri plus alpha lambda plus beta times rj. Note that there is rj here, so we collect the coefficient of rj. We get this alpha ri plus alpha lambda plus beta times rj equal to alpha beta belongs to R. So this is also all possible linear combination of ri rj. This is also all possible linear combination of ri rj. Therefore, span of this vector and the span of this vector are same. So altogether, what we are understanding from row operation is, this operation says that the places at which the rows are present, it is not important. You can put any row in any other place you want. This means that, so by this operation, vector one vector might change to another vector, but the row space won't change. Okay, that is the important thing. Once you understand this, the options are now uh, very easy to solve this problem. Let's see. So now first option says that the first two rows of A are linearly independent. Okay, so if you consider this matrix A, for this matrix R is row equivalent matrix. By swapping the first and fourth row, we get this matrix. Therefore, A can be this matrix, but the first two rows of A are not linearly independent. Okay, therefore, first option is false. Okay, next we come to the second option. The last four rows of A. Note that this is one possible A. So here I have swapped first and fourth. You can swap the first and last. So many matrix can be similar to this matrix R. So you can permute the rows in any way you want. All those matrices will be row equivalent to this matrix. After that, you can apply these two operations also. So that matrix will also row equivalent to this matrix. Okay. So using that observation, now we want to solve the second option. The last four rows of A generate a space of dimension at least 2. Okay. So let's write A. A equal to first row, second row, third row, and fourth row, fifth row. So A has 5 rows. Okay. Now they are saying that if you look at the last 4 rows, so these 4 rows you take, then they are saying that they generate a space of dimension at least 2. Okay. Now again we come to our observation. We just observed what this row operation does. We notice that, so these last 4, that positions of the vectors doesn't matter. Okay, so for example, here you pick any 4 vectors that you can put it in this place. That is our first observation. Okay, we saw that you can permute the rows in any way you want. In particular, you take these first 4 rows, you can send it to these places by using the first operation, and the fifth row goes to the first place. This is one possible. Okay, similarly, you pick any 4 and that can be put it in the last 4 place. Therefore, this option says that the last 4 rows of generate a space of dimension at least 2 actually means that if you pick any 4 rows here, okay, you pick any 4 rows here, that will generate a space of dimension at least 2. That is what it means. Okay, after that you can apply these two operations, but these two operations is not going to the, it's not going to change the dimension of the space, it's just span, because we just saw that these two operations preserves the row space. Therefore, what really matters is this operation as long as dimension of the row space is concerned. Therefore, this statement actually means that you pick any 4 rows here, it will generate a dimension at least 2. That is true, because if you pick 4 rows here, maximum 2 rows can be 0. Okay, and if you look at other 2 rows, they will be linearly independent because these first 3 vectors are linearly independent. Therefore, the dimension of the, therefore the row space of A generated by this last 4 rows. In other words, the row space generated by any 4 rows here will be at least 2. Therefore, this option is true. Okay. Okay, so this question for the columns is much simpler. So the first 2 columns of A are linearly independent. The last 4 columns of A generate a space of dimension 3. These 2 options can be answered very more easily. Let's see why. So we claim that elementary row operations map independent columns to independent columns, dependent columns to dependent columns. That is what we try. Let's see why. So you take A to be an arbitrary matrix, okay, and I take the columns of the matrix A to be C1, C2, etc. Cn. If A is a n by n matrix, then these columns are n by 1 vectors. I take B to be an arbitrary invertible n by n real matrix, and I take its rows to be row 1, x, R1, R2, etc. Rn. If it is, these are rows means they are 1 by n vectors. Okay. Now I want to multiply the matrix B times A. Okay. How do I multiply two matrices? I take the first row and I multiply the with the first column. Okay. Note that that is same as taking the inner product of this vector with the inner product of this first column. Okay, so I denote it by inner product R1 comma C1. Okay, maybe we need to put a transpose here, but that is fine. The concept is clear. So similarly, for the next entry, what we do, we take the first row and we multiply the second column, then first row into third column, then first row into fourth column, and so on. So multiplying B, when you multiply BA, so each entry is this inner product, inner product R1 comma C1, where Ci's are columns of A, Ri's are rows of B. Note that that is a notational, that is what notation we are using. Therefore, BA is nothing. BA is given by the entries of BA are given by these inner products. Okay, that is one observation. Now let's pick C1. Okay, so C1 is the column of A. So it is a n by 1 vector and B is a n by n matrix. C is a n by 1. C1 is a n by 1 vector. So what we can do, this we can multiply them, or we can find the image of the column C1 under the linear transformation B. So what we do, so if you have a matrix and you have a vector, how do you multiply them? Again, first row into this column, first row into this column, first row into this column. That's what we do. Basically, that means that this first row inner product with this column. So inner product R1 comma C1, then inner product R2 comma C2, etc. Inner product Rn comma Cn. So we observed that this when you multiply two matrices B and A, this first column is nothing but the matrix B acting on the first column. Therefore, we get B times A is nothing but the matrix B acting on the first column of A. Then the second column of BA will be the column of second column of A acted by the matrix B, and then last column of BA will be you act the last column of A by the matrix B. That is the This is what we observe. Okay. So now it is easy to prove our result. So we claim that if Ci1, Ci2, Cik, this is some columns in the matrix A. Okay. Suppose these columns Ci1, Ci2, Cik, these columns are linearly independent. Then we claim that BCI1, BCI2, BCIK, these columns are also linearly independent. Okay, so that means that if if some columns in A are linearly independent, then the corresponding columns in BA are also linearly independent. So let's see why so. So to prove BCI1, BCI2, BCIK are linearly independent, we take the linear combination is equal to 0. Since B is linear, you can take the we can take the coefficients inside. That means that B of this vector equal to 0, but B is invertible matrix. Here only we are using the factor that B is invertible. So if it is an invertible matrix, then its kernel is singleton 0. Therefore, this vector has to be 0. Therefore, we get this relation alpha Ci1 plus etc. Alpha k Cik equal to 0. We assumed these vectors are linearly independent. Therefore, we get all these coefficients are 0, scalars are 0. Therefore, these vectors also linearly independent. So basically what we have proved is if some columns are linearly independent in a matrix A, and if you calculate B times A, if B is invertible, then the corresponding columns in BA are also linearly independent. Now we use this result to deduce our result. Note that so there are three elementary row operations we saw. So we observe some result in case of 3 by 3 matrices. So suppose you want to interchange second row and the third row. Okay. What you do is you look at the 3 by 3 identity matrix and you apply this operation to the 3 by 3 identity matrix. So what happens? The second row and the third row I have swapped. Okay. So now applying this operation to any matrix is equivalent to pre-multiplying this matrix. Okay. So not that. So I multiply this matrix by this matrix. I am pre-multiplying. Pre means we are multiplying from left side. So if you multiply this matrix by this matrix, you get this matrix. Note that here the second and third row get interchanged. Okay. So this operation can be obtained by pre-multiplying the corresponding elementary matrix. So this is called the elementary row matrix corresponds to this elementary operation, elementary row operation. Similarly, if you want to do this in a second, another row operation, first you apply this row operation to the identity matrix, you get this matrix, and pre-multiplying by this matrix to an arbitrary matrix give you the this operation obtained applied to this matrix. Okay, therefore what we are observing is also observe that these elementary matrices are always invertible. Observe is doing this operation is same as pre-multiplying by an invertible matrix. Okay, but now we just saw that if certain columns are linearly independent in A, then that columns are linearly independent in BA also. Therefore, elementary row operations are equivalent to pre-multiplying an invertible matrix. Therefore, by the elementary row operations, invertible columns are is going to invertible linearly independent columns are mapped to linearly independent columns. That is what we have proved. So now we can go to our problem. So first two columns of A are linearly independent. Like R is row equivalent to A means from in A you keep applying various row operations. Finally, you will get this matrix, right? So whenever you do a row operation, you apply that corresponding, you multiply, pre-multiply by the corresponding elementary row matrix. Okay, so here I multiply k up elementary row operation to get the matrix R. Okay, now note that product of invertible matrix is invertible, so this matrix is invertible. So from this you can write A to be what you can do, ek inverse, ek minus 1 inverse, etc., etc., e1 inverse times R. Okay, and again these all these matrices are invertible, product of invertible matrices is invertible. Therefore, if certain columns are linearly independent here, that columns will be linearly independent in A also. Note that here these two columns are linearly independent and this is an invertible matrix. Therefore, columns in A will also linearly independent. Okay, so therefore first option is true. The first two columns of A are linearly independent. Similarly, the last four columns of A generate a space of dimension 3. Okay, so here the last four columns of R generate a space of dimension 3. Now note that this is again an invertible linear transformation. Okay, therefore if this spans of a space of dimension 3, its image also will span dimension 3. Therefore the last columns in last four columns in A will also span a space of dimension 3. Okay, therefore that answer is also true. Okay. Okay guys, if you learned something new from this problem, please click the like button and share with your friends. Thank you.